Okay, hi everyone, it's Mr. Zhang here. I'm going to be doing some of these problems with you. I think I'm just going to do probably two problems. Sorry, here, two problems. It's because the methods are the same. So here's here's what you need to know, right? So one, we're going to use this equation equals mc squared. Of course, we're not actually using this one. We're using a variation of it, right? Where it's delta m times c squared instead, where delta m is essentially your final mass minus your initial mass. Okay, so this will be our initial mass, and then this would be our final mass, and this is the answer. Okay, so this is the answer. So for problem A and problem B, they're basically the same problem, and you're using the same method. Right, so once we do this, then two, we can do conversion, right? Conversion to energy. All right, we're gonna find the unit in AMU, right, or atomic mass unit U, and then we convert that to a mass, right? We convert it to MeV or joules, or sorry, kilograms. Okay. So let's get started. I'm gonna choose a different color here. So first we have to calculate we have to figure out what our initial mass is. So in this case, it's gonna be 235.0439 U plus the mass of a neutron, which is this. And you can find that in the IB packet, 1.008665 U. Okay, so you add this together. So remember, this is our MI. So let's do our M final, right? So it's going to be 91.92615 U plus, maybe I should have done it in a different color, sorry, plus 141.9164 U plus, in this case, it's going to be 2 times 1.008665 U. Okay, like that. Okay, so we're going to add, so we're going to do this calculation. Let's see, so I got that. Okay, so if you do this calculation, you should get, right, so I got delta M is equal to, right, so remember this is our MF. So if we do MF minus M initial, so if we do this calculation, you should get, I got a negative number, right? 0.92679, right? Like that. Now, or you can say that it's positive. It doesn't really matter as long as you know that the energy that you calculated is the energy that is released. Okay. So we take this number, and now we use our conversion factor. So 0.192679 U times, in this case, I'm going to do 1 U, and I'm going to do 931.5 mega electron volts now over C squared. And you might be like, where is this number coming from? It's just a conversion unit, but I guess I'll write it up here. It's just 931.5 MeV / C squared. And then 1 U is equal to, I believe you should have these numbers like in your IB packet somewhere. But 1 U is also equal to 1.66 times 10 to the negative 27 kilograms, right? So that'd be useful for finding, right? So this one is useful for finding joules, and this one, oh, leave me alone. And this one is useful for finding mega electron volts. Okay. So I'm going to use the one for mega electron volts because it's just an easier calculation. All right, so we do this multiplication. I need a calculator. So 0, sorry, I'm going to type this in the calculator. 92679 times 931.1. Okay, so I get 179.48048 mega electron volts per c square. Now we're not done yet, right? Because we have to like take this number and we have to plug it into our equation, right? So what we found is like this. Now we need to use this. Now we need to use the entire equation. Right? The entire equation. So you take the one. I don't want to rewrite it, so I'm gonna go like this. I'm gonna be like this. Duplicate. I'm gonna do that, and then I'm gonna multiply it by c squared to get E. And we find that E is equal to 179.48048 mega electron volts. There we go. Now this is only in mega electron volts, so we have to do the other one. Now what you can do is like basically the same thing over here, right? This part. But instead of mega electron volts, you're going to use 1.66 times 10 to the negative 27 kilograms. Or there's actually another method, and I'm going to use this method because it's pretty easy. I don't know, a little bit easier. But essentially, because the energy is in mega electron volts, there's something that you should know, and it's that 1 eV is equal to 1.60 times 10 to negative 19 joules. So I can just convert between energies instead. And this is a little bit of a cheat code that I'm just going to use. But what you should do is like this method, you know? Use that method. But I'll show you this one in case you want to do this one. But essentially, right now this is an 1 EV, but I want it to be 1 mega EV, you know? So what I do is I multiply this by 10 to the 6. 1 times 10 to the 6. And so if I do it on this side, I have to do it on this side as well. So it's 1.60 times 10 to the negative 19 joules, which becomes 1.60 times 10 to the negative 13 joules. Just trust me, that's the right answer if you don't know how to do math. But it is, right? Because you're just taking 10 to the 6 and you're multiplying it against this. And when you multiply, you want to add exponents. The exponents add. Okay, so, right, so now I have, now I have 1.7948 MeV over 1 times 1 MeV. Right, so you can see how the energies cancel, and now I'm going to put this here. So if I do this multiplication, it'll give me the answer for joules. So I'm going to do the multiplication for joules. 1.60 times 10 to the negative 13. So I get 2.871687 times 10 to the negative 11 joules. Okay, if you use like this method, right, but you replaced it with kilograms instead, like you replaced it with this, it should still give you the same answer. And let me just double check my answer here. Yeah, so it should still be correct. Okay, so B, it's the same process. So what I want you to do is repeat the steps. Is there another one that I want to do? Number 2. Oh, it's also asking like what type of reaction it is. This one is a fission reaction. And of course this one is also a fission reaction. Okay. Take a look at this. Yes, this is a fission reaction. Fission. Use the data below to find the energy in MeV that's released in the reaction. Same method as the above. Same method. Okay, I think I'll do this one. It's a little bit more tricky, and you have to like think about it. Okay, in the reaction, this, okay, in this reaction, right, in this reaction, energy is released. Oh, plus energy is released. State the type of reaction. I'm pretty sure this is a fusion reaction, right? You can see how the nucleus of these, right? So we have 2 hydrogen plus 3 hydrogen gives us helium, right? The nucleus is increasing, and you get N plus energy. So let's draw an arrow on the graph below to indicate which direction this reaction is going. Well, it's going to go from here to here, and we know that's from the thing that we learned in class. That's fusion. All right. Here we go. It says calculate how much energy is released using the binding energies and MeV and in joules. I'm probably just gonna do an MeV. You guys can do it in joules. Yeah, same method, pretty much. Okay, so what we want to do is we want to find, again, right? Our goal is to find delta M, and delta M is final minus initial. So that's gonna be, okay, 4 He plus 1 neutron plus some energy. Okay, so right, so what we want to do is we want to take 4 and want to multiply it by 4.002602 U, right? That's this number right here. All right, there's 4 of them plus 1 neutron, 1. Oh, I think I'm just gonna write the number here. What's the number again? 1.00. Okay. 1.008 U, right? So right now I'm doing MF. Okay. Next one, let's do it in green. So I have 2, and 3. Okay. This will be 2 times. Whoop. That 2 is so ugly. 2 times 2.013555321. What the heck? 2. There's so many numbers. I hate this. This is so stupid. There's so many numbers. Kind of annoying. And then I think it's 3. Yeah. 3. Wait. No. Wait. Is this wrong? Oh, that's stupid. Okay, sorry. This is not 4 helium. Oh my god, this is kind of dumb. Okay, sorry, it's not 4 helium. I just realized, like, it didn't, like, so this is supposed to be, like, H2 plus H3. I just realized that, sorry. I don't know why the format didn't carry over. Okay, that's not great. Sorry about that. Okay, here we go. And then, of course, we want to delete this one as well. Right, get that. The green one is 3.0160492 U. Alright, so this is our MI. So let's do this MF minus MI. I'm going to do this on calculator. So if you do this on calculator, you should get something like this. Give me a second. It's kind of annoying, right? But you should get something like this. Negative 0.018. 3. 5. 4. 1. 2. 7. U. Wow, this is so ugly. Okay, so we get this, and now we do the same thing, right? We're going to do a conversion. So I'm just going to say delta M is going to multiply by 1 over, U, and then I'm going to say 931.5 MeV. Okay, and if you do this calculation, right, so you take this number, so we just take this number and we just put it here. We substitute that in, and you should get negative 17.007943695 MeV over c squared. Now you take this number and you multiply it by c squared. Bam, that cancels out. So your E is this. 5 MeV. Bam. Okay, so that's pretty much it. Right? So, folks, I want you to do the rest of these problems. Try them by yourself. So you're kind of doing 3 problems. All right, have fun. They are just okay. So the thing about nuclear physics is that it's just the calculation is just tedious. That's really it. But all the numbers really do matter. So you want to like make sure you include all the sig figs as much as you can. All right, thanks for watching. Bye. Hopefully it helped.